I don't know where I am. I think I got lost in an apartment store. Okay, so in our prior examples and videos, we have talked about calorimetry, which is looking at heat or heat energy moving from one object to a next in a closed, isolated system. In our last problem, we took a look at the hot dog lab, where you find the specific heat of a hot dog by putting it into some water inside a calorimeter, okay, or a nice styrofoam cup. Um, when we did that, we saw that hot items are gonna, cool down, and then the cooler items are gonna heat up and reach some sort of equilibrium temperature. One of the things that we haven't talked about yet, though, is phase changes and what happens whenever we melt ice into water or vaporize water into a gas, or even go the other way. We condense water from a gas into a liquid, or we freeze that liquid. So what is happening with energy transfers through all of that? And this deals with the idea of latent heat. So let's roll over to some graphs real quick and see kind of what's going on in the world of latent heat when we start looking at things. This graph up top is dealing with temperature and enthalpy. And really, instead of thinking about enthalpy, let's not worry about that chemistry nonsense. Let's just really think of this in the bottom here as heat that is added to a system or taken away from a system. Okay? What we see here, though, is if we're in Celsius, we see that if our temperature is less than 0 degrees Celsius, we have a solid liquid. For, water becomes ice. And if we increase the temperature of that solid, we still have ice. This is actually a really, really cool thing. You can have ice that is at negative 100 degrees Celsius. It's ice. You could have ice at 0 degrees Celsius. It is still ice. The difference is if you're using this ice in your cooler, the negative 100 degrees Celsius ice is going to last a lot longer than the 0 degrees Celsius ice. The reason being is that this 100 degree or the negative 100 degrees Celsius ice, you have to warm it up. And did I write warmth? What kind of word is that? You have to warm it up. You have to warm it up, and you have to melt it. Where once it hits 0 degrees, you just have to melt this ice. Okay. You can tell ice that isn't very good because whenever you hold it in your hand, it feels like not slimy, but like it's immediately wet. If you've got very, very cold ice, when you pick it up in your hands, like it's dry. It doesn't do anything because you're still warming the ice up. So what we could do here is if we have cold ice, we wanted to heat it up. We could, put it on a fire or something like that. And we begin to heat the ice up. In doing so, we are changing its temperature. Once it gets to 0 degrees Celsius, though, when we add more heat to that ice isn't going to heat up. That ice is going to hold at 0 degrees. So we have, if this is at like negative 100 down here, we've heated the ice, and now that ice is holding at some temperature, 0 degrees Celsius. It's going to hold there. What it's doing here is it is melting. Okay, this ice is now melting, or if it was a liquid, it's freezing if we go the opposite direction. Once all of that ice has melted, then we can begin to increase that liquid, that water's temperature. We can begin to rock that temperature up like this. This only occurs when all of that ice has melted. Assuming a nice, well-mixed substance, we're not talking about like if you've got ice in the Antarctic, but I'm here in my house, like how can I heat the water up here? Like those are different systems, right? But if the system is together and everything is nice and well-mixed, then everything has to melt before you can heat it up. But once you do that, you can begin to heat it up. So we've melted everything, we can then heat it up and get to some higher temperature. Once we get to 100 degrees Celsius, or like 99.9839 for specific water and whatnot, we'll just call it 100. Then we can't actually heat that water up anymore. Okay, that is the hottest temperature for liquid water. You cannot have liquid water hotter than 100 degrees Celsius to 12 degrees Fahrenheit. Ugh, Fahrenheit. Blah. Don't ever say those words. This is actually a really nice thing for baking. For some methods of baking, you'll actually use a water bath, and especially for cheesecakes, you put your tins in a water bath, and this makes sure that you don't over heat your whatever you're baking here, like a cheesecake. If you heat them too quickly, they'll crack. So by putting them in a very hot oven, but keeping them in a water bath at 100 degrees, they're not going to overheat and crack. Very important for bakers. But when this happens here, what starts to happen is you start boiling that water, okay? And when you start boiling the water, you begin to vaporize it. That water gets so much energy into it that it begins to release as a steam. And it's only once we vaporize all of that water can we actually start increasing the temperature of steam here, okay? So we get, this is a vapor. Here we're melting. And then up here, this is all steam, as we see in this kind of picture here. And this actually means that, if you've ever watched a movie and a pipe kind of explodes and like steam hits someone's face, steam burns are way more dangerous than sticking your hand in a vat of boiling water. Because steam burns, they don't have to be at 100 degrees Celsius. They could be at 600 degrees Celsius. Like you could get a steam burn and your arm like melts. That's super, super dangerous. So steam is much more dangerous than just water vapor. You can heat steam up, to arbitrarily high amounts, and then at very, very high values, like some other stuff starts breaking down in it, gets so much energy. But, if you asked me the question, would you rather stick your hand in a vat of boiling water, or would you stick your hand in front of a hot steam pipe? I'd pick the water every day, because I have no idea how hot that steam pipe could be, and it's at least at 100 degrees. So this is the idea of phase changes as we add heat or, some heat energy Q with respect to temperature, okay? And because we are still adding energy through these phase changes, these meltings or these freezings or these boiling vaporizations or condensings, we need to account for that energy. And the way we do that is through latent heat. So each of these regions here, the vaporization or the melting, has a latent heat. And we designate latent heat with the symbol L. We can say the latent heat of fusion is LF. This is going from like a solid to a liquid, or, vice versa, going backwards, liquid to a solid. That's the latent heat of fusion. Also a great Metroid game. And we also have a latent heat of vaporization. And this is for going from a liquid to a gas, or vice versa back. And like I said, this is for vaporization. Okay, so these are extra energies that we have to account for. Most of the values for our latent heats are just kind of found in a book. One of the values we will need often, though, is the latent heat of fusion for water. It is 333. Many different ways to write this. I like to write it joules per gram. Okay, some people write this as kilojoules per kilogram. The kilos go away and you just get joules per gram. So this is the latent heat of fusion for water. That's a very, very important value. Other latent heats, if you're looking for them, you can just find them in tables in any textbook. We'll start digging through some of them as we continue out through this unit. Okay, so this is the idea of latent heat, though. In our next video, we'll take this idea of latent heat and we'll actually start pushing it into an example problem. We'll see how we can use calorimetry plus our latent heat here in order to figure out just what temperatures things should wind up to be. But for right now, adios and take it easy.